average speed of particle, square root of 8 RT over pi m. So the key thing is, as you increase temperature, as T increases, you see that the velocity increases, right? For a given temperature, if you increase the mass of the particle, the velocity decreases, right? So at the same temperature, hydrogen molecule move much, much faster than chlorine molecules, Cl2. Bromine molecules move even slower because they are even heavier. And iodine molecule move even slower in the gas phase at the same temperature, right? So the mass of the particle and the temperature affects the velocity. Now, this is just for the averages. All the molecules are not moving at the same speed. And this is what is shown here on this Maxwell-Boltzmann distribution. At low temperature, what happens is molecules tend to move more or less at the same speed. You see that the fraction of the molecule that have a given speed is distributed over in a smaller range of speed. As I increase the temperature, let's say to this intermediate temperature here, you see now the range of speed increases. And as I go to even a higher temperature, the range of speed now increases up to here. Now, the range of speed increases as I increase the temperature, but notice also that the average, or if I take the average, for instance, to be represented by the peak position, which is the most probable velocity, that's most of the particle will have that speed. At low temperature, it's here. As I increase the temperature, it's somewhere here. And as I increase the temperature to even more, now it's here, So you see how the average speed increases when I increase the temperature, And here I looked at average simply by defining the position of the peak of this distribution. And the same thing, if I have a high molar mass particle, bigger, heavier molecules tend to have a narrower distribution of speed than small molecules that have a broader distribution of speed. Now, this is all based on this equation right here that we've defined before, because the way we've talked about energy here is we talk about kinetic energy. So we can say, well, molecules have different kinetic energy, and as I change the kinetic energy, I'm going to change the population, of course, of the molecule. So this equation that we've defined for quantized energy levels and so on, of course, also applies to the kinetic energy of molecules. And when we use it in that context, then we get these curves, I'm not going to ask you to derive that. I just want you to have an idea about these plots, showing that as I increase temperature, the range of velocities molecules can acquire is broader, and that the average occurs at a higher velocity. Initially derived by Boltzmann, the Boltzmann equation, but Maxwell is the guy who applied that to gases and then derived that. The last slide is a simple application of what we talked about, paying attention to the units. And the key thing here, there are two key things here. One is I want you to remember that temperature is always in ppm written with the Kelvin symbol. So if we use all SI units, R is going to be 8.3145 in SI units. And then pi doesn't have any units, and M, and this is where people make that mistake, M is in kilograms per mole, right? Because the SI units of mass is kilogram, not gram. So pay attention to these two things here, the Kelvin, the kilograms per mole, and using the SI value of R. And if you do that, then you're going to get the right speed. You may want to try and see what happens if you had used, this is for helium, if you had used 4 grams per mole instead of 0.004 kilograms per mole, you would see you would get a much smaller value. And that's a typical, thousands of meters per second or hundreds of meters per second is a typical speed for molecules in the gas phase.